Oxygen dictates the structure of aquatic ectotherm communities. Breathing underwater is challenging. Oxygen is essential for burning food to provide energy and support animal life. Underwater, there is 33 times less oxygen, and the diffusion or movement of oxygen molecules is greatly reduced by a factor of 300,000. Consequently, many aquatic animals have special adaptations to extract oxygen from the water, such as gills. Temperature controls on oxygen dynamics. Ectotherms, or cold-blooded animals, require more oxygen as their habitat warms up. At a certain temperature, an animal can no longer supply its oxygen to its tissues, effectively setting the upper temperature that a species can tolerate. Thus, it is important to know what components control the oxygen that is available to an animal and how these components change with temperature. Ecologists commonly express oxygen in quantities. Less oxygen can dissolve in warm water, hence there may be a double jeopardy with increased temperatures. Physiologists emphasize differences in pressure exerted by oxygen, which does not change with temperature. However, at high altitudes, the partial pressure of oxygen is lower. A third component is the diffusion, or movement of oxygen molecules. At higher temperatures, oxygen diffusivity is increased. Recent research reunites these viewpoints, revealing that oxygen is controlled by three components: both solubility and pressure, as well as the diffusion speed, which increases with temperature. An oxygen index incorporating all three components shows that oxygen availability increases with temperature. A mismatch between an organism's oxygen demand and the oxygen available in the environment arises because oxygen demand increases exponentially with temperature and hence faster than increases in supply. Test 1. Going up into thin air. A perfect test is provided by mountain streams. As one goes up a mountain, pressure decreases, but the cold water at high altitude can hold more oxygen as solubility increases. The diversity of aquatic insects is related to oxygen. More species are found under conditions of higher oxygen. Concentrations explain some of this variation in species richness, as did pressure, but an oxygen index incorporating both solubility and pressure, as well as the diffusion speed, was superior, explaining 35% of the variation in species richness. Test 2. Polar gigantism in an oxygen low. The finding of reduced oxygen availability in the cold challenges the traditional explanation for polar gigantism, where high oxygen concentrations at low temperatures were thought to allow for larger body sizes. Instead, oxygen availability is lower in the cold. Per time unit, more oxygen is available in warmer waters due to increased diffusion. Oxygen demand increases with temperature, and because of marked differences in oxygen demand, gigantism may arise in the cold, where oxygen supply is high relative to demand. Body sizes could be accurately predicted from oxygen supply and demand when using the index as a measure of oxygen supply. Tackling global environmental challenges. Incorporating solubility, pressure, and the speed of diffusion provides a better understanding of what limits oxygen in nature and how oxygen affects patterns in body size and species diversity. Under this new view, changes in environmental oxygen availability and organismal differences in respiration physiology can considerably affect the thermal responses of species. Both evolutionary processes altering an organism's oxygen demand and efforts to improve water quality and water oxygenation can make a substantial contribution towards combating climate change effects. The new index reconciles different viewpoints held by ecologists and physiologists. It enables a better understanding of how oxygen supply matches a species' capabilities and constraints. Such understanding is imperative to tackle key scientific questions and global environmental challenges.